Hello everyone, welcome to lecture 31 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be discussing on 2D model of microwave antenna with one layer metamaterial. So, it is basically the continuation of the previous lecture. Here is the lecture outline. So, we will complete our discussion on this 2D model of microwave antenna with one layer wire composite or the metamaterial structure as a substrate that we started earlier, and then we will also look into different design models of microwave antenna. So, in the previous lecture we studied about the electric intensity vector in region 1 and region 2. Okay. So, now in this lecture we will start with the magnetic intensity vectors. Okay. So, you will see that the approximation for the magnetic intensity vector in this first and second space domains are defined using Faraday's law. So, in the first domain, that is with the x within 0 and 2h, that is here where the wires are basically embedded in the substrate. So, in that medium you can write the magnetic field H1 xy equals minus E naught, that is the incident electric field, divided by Z1, that is the impedance in the first medium, okay, times E1 plus xy into sin alpha, this angle, times x naught, that is basically x cap, okay, minus, that is the unit vector along the x direction, minus E1 minus xy times cos alpha into y naught or y cap. Okay. In the second domain here, where x is greater than 2h, the expression can be written as h2 xy equals minus e2 xy by z2. So, z2 will be the impedance in the second domain. So, if it is free space, you can consider this as z naught, okay, for this example. So, that is sin theta times x naught plus cos theta times y naught. Okay. These are basically the unit vectors. Now, what is E1 plus minus xy? So, you can see that that can be written as e to the power I k1y sin alpha times e to the power I k1x cos alpha plus minus r, that is basically the reflection, okay, and coefficient, and then you have e to the power minus I k1x cos alpha. Okay. So, this is basically the reflection term, okay, that has to be considered. Now, let us present the current flow on the patch in the form of J, that can be written as J delta x minus 2h times z naught, that is basically the z cap, right. So, you can write this as minus J naught delta x minus 2h into e to the power minus k2 y sin theta times z naught. So, here what is this z naught? It is basically a constant to be predetermined, and then you have k2 appearing, that is basically k naught, which is the wave vector or wave number, you can say, in the second space domain, that is for x greater than 2h, which is free space in this particular example. And then this guy is nothing but your unit vector in the z axis, right. So, this notation is basically taken from this book. Okay. Now, what is this delta function, right? You see a delta x minus 2h, that is a direct delta function, which tells you that it is 0 everywhere except for x equals 2h. So, that implies that the current density is basically confined in the plane x equals 2h, right, in this particular plane only. Now, here couple of unknowns are there, like E naught, A and alpha. So, these are to be calculated by imposing the boundary conditions for the tangential electric and magnetic fields to be continuous at the interface at x equals 2h. So, when you put those boundary conditions, okay, they will look like E1 you calculate at x equals 2h, that should be equal to E2 as well at the boundary, okay. And also, okay, from the magnetic field, the curl Okay, so you see x cap or x naught, okay, and then you take the difference in the magnetic field, okay, H2 minus H1 at this particular plane will be nothing but the current density, okay, or you can say this is basically the current flow, right, in and that will be in the z naught direction, okay, or the z cap. So, z is basically the direction of the length of the wires which are put in the substrate. Now, once you substitute those equations and the equations from the electric intensity vector, these ones that you have seen in the previous lecture, okay, for both the domains into these expressions 5 and 6, that is your boundary condition, you will be able to obtain what is E naught. So, E naught can be written as J naught Z2 Z1 divided by Z1 cos theta E1 plus and you are taking it at x equals 2h, okay, and y is considered 0. So, that is x y basically plus Z2 cos alpha E1 minus and then at the same point. Okay. So, what is alpha here, or you can say cos alpha can be written as square root of 1 minus sin square theta divided by epsilon m mu m. So, that is how you can obtain what is alpha, right. So, from that you can also obtain what is the efficiency of the antenna. So, you can evaluate this from this particular formula, eta equals P rad divided by Pt. Okay. So, what is P rad? P rad is basically the total radiated power, okay, and Pt is basically the power, total power delivered to the antenna terminal via the transmission line. So, this can also be written as real of Pr, that tells you that Pr is basically the complex input power of the antenna, right. So, this complex input power of the antenna Pr can be determined as Pr equals minus half surface integral over the patch. You have E2, that is basically the incident electric field in that region, okay. Then you have J conjugate ds. So, if you work it out, it can be written as J naught S by 2 A. Now, if you compare this, you will say that A is nothing but minus 1 by J naught S surface integral of E2 times J conjugate, okay. So, you can say that A is basically the normalizing coupling coefficient between the incident electric field E2 and the complex conjugate of the current distribution J. So, you have this J conjugate here, which is calculated over the surface of the patch S. Now, it is assumed that the imaginary part of this PR, okay, is due to energy that is mostly stored in the vicinity of this wire grid and is just partially stored in the vicinity of the antenna patch, okay. So, imaginary part is mainly lying with the wires. So, in that case, the total power delivered to the antenna terminal via a transmission line. So, you can calculate that as Pt, the total power, and S is nothing but the area of the patch, that is W by L, okay, or W cross L you can say, and from that you can obtain that the total power Pt can be written as P rad plus P ohm. Now, what is this P ohm? P ohm is basically the power dissipated due to ohmic loss, okay, and that you can calculate as using this formula, which is P ohm equals half, again surface integral of the current distribution J. So, you have mod J square, okay, into R, okay. So, Rp is basically the ohmic resistance of the antenna patch. So, this is typically nothing but I square R, okay. So, I you are calculating taking the surface integral of the current density, right. Now, throughout this study, we consider a perfectly thin copper patch along with Rp, which is the ohmic resistance that you have seen, given as Rs times S. So, you can take Rs to be equal to square root of omega mu naught divided by 2 sigma I. So, Rs will be nothing but your sheet resistance or surface resistance. Okay, you can say this is the surface resistance of a highly conductive non-magnetic metal in microwave frequency range. So, once you substitute 9 and 11 into equation 10. So, you can see here 9 and 11 into equation 10, because you are interested in finding out PT. You will see the PT takes this particular form, J naught S by 2 times real of A plus J square S square by 2 square root of this term, which is omega mu naught by 2 sigma I. And substituting this and 9 into equation 8, you can find out. So, equation 8, I will just show you what is that. So, this was your equation 8 that was giving you the efficiency of the antenna, where you required this real power of PR by PT. So, now you have obtained both. So, you can get the efficiency looking like this, which is 1 over 1 plus J naught S real of A square root of omega mu naught by 2 sigma I. So, from the conductivity of the material also you can relate to the efficiency of the patch antenna. Now, we need to calculate the normal edge gain and the directivity. So, to do that, the radiated far field intensity needs to be plotted in the spherical coordinate system, which is shown here. So, you can see that this is the spherical coordinate system. So, at any point this is the radial direction coming out, and this angle is called theta, and this is the azimuthal angle phi. So, you can consider this direction as theta equals 0, that is along the z direction. So, on the opposite side you have theta equals 180 degree. Again, this is considered to be theta equals 90 degree plane, and then phi equals 0. So, when you come to this side, here theta is also 90 degree, phi is also 90 degree. When you go to the other side, your phi is 270 degree, right, and theta remains 90 degree only. So, we can assume antenna to be here, and you can use the spherical coordinate system to find out all these parameters like normal edge gain and directivity. So, as per Balanis, the electric field components are given by E theta and E phi. So, E theta can be written as I k naught e to the power minus I k naught r divided by 2 pi r times 1 plus cos theta by 2 f, which is a function of theta and phi both, and then you have sin phi. For E phi, everything else remains same, just that you have cos phi component here. So, what is r? R is basically telling you the radial distance, phi is basically giving you the azimuthal angle. So, it starts with x axis. So, you basically measure it from the x axis in the xy plane. So, you are basically in this xy plane and you are measuring it. Theta is called the polar angle, and that you measure from the z axis. Now, the expression for the radiation pattern. So, here you will see that f theta phi is basically your radiation pattern, and that you can calculate using this formula. So, f theta phi can be obtained as again integral over the surface of the patch E2, you are calculating at x equals 2h plane, y. So, these are the functions, this is basically x y, right, and then you have e to the power I k2 y and plus e to the power I k2 z. So, and then you have dy and dz. So, when you compute this, you basically get 4 modulus of A times S, that is the W cross L, and then you have 3 sinc functions multiplying each other. So, sinc L by lambda by 2 cos phi minus 1 sin theta, then you have sinc L by lambda by 2 sin theta sin phi, and then you have sinc W by lambda 2, which is sin theta cos phi. So, here you can see that lambda 2 is basically nothing but the lambda naught in the second space domain, right. And we are using sinc function here. You consider this as sinc x will be equal to sin pi x by pi x. So, that is basically the normalized sinc function, okay. And this values, so these are basically k2 y. So, k2 y is nothing but k naught sin theta sin phi, okay, and k2 z is nothing but k naught cos theta. So, that you can obtain from this previous figure as well. So, with that you can write down the expression for radiation density that can be given in this particular form. So, you can write u theta phi will be equal to k naught square divided by 8 pi square z naught times 1 plus cos theta whole square by 4, and then you have modulus of this radiation pattern, okay. So, modulus f theta phi whole square. From that you can obtain the expression for the directive gain as d theta phi. So, that will take this radiation density into account. So, you have 4 pi u theta pi divided by real of p r. So, when you expand it, you will get 2 k naught s modulus of a whole square divided by pi z naught, okay, times 1 plus cos theta whole square divided by real of a times sinc square. You have this 3 sinc function, that is L by lambda naught cos phi minus 1 into sin theta. So, here you have basically sinc square, okay. So, the 3 function are basically sinc square. So, this is sinc square L by lambda naught sin theta sin phi times sinc square W by lambda naught sin theta cos phi. So, as you can see from this equation that the maximum value of the directive gain can be achieved when you have theta equals 0 degree, right, and its value can be written as d max. So, that is basically giving you the directivity, and that comes down to this equation, which is 8 k naught square divided by pi z naught, okay, 8 k naught square divided by pi z naught, and then you have s a calculated at theta equals 0 whole square of that divided by real of a calculated at again theta equal 0 degree, right. So, from that you can find what is the maximum directive gain, okay. So, you can also find out the maximum gain that can be written as G max, which is nothing but the efficiency of the antenna times the maximum directivity. So, that turns out to be 8 k naught square divided by pi z naught, and then you have S modulus of A calculated at theta equals 0 whole square of that divided by real of A theta equals 0. So, that is basically your D max, and then you put the eta, which is 1 over 1 plus j naught S divided by real of A at theta equals 0 square root of omega mu naught divided by 2 sigma I, okay. So, if you take into account equation 16, that is this particular expression for radiation pattern, okay, you can derive the expression for the normalized gain in the form of G theta phi, which will be like this is the normalized. So, you are basically dividing it by the maximum radiation pattern. So, you see 1 plus cos theta whole square by 4 divided by this fraction, okay. So, that is modulus of f theta phi whole square divided by f theta pi max whole square. So, it gives you 1 plus cos theta whole square by 4 divided into sinc square L by lambda naught times cos phi minus 1 into sin theta times another factors sinc square W by lambda naught sin theta cos phi. So, now that the expression for the normalized gain you can obtain along the 2 principal planes that can be given in this particular form. So, if you consider the H plane, you can set phi equals 0. So, that will basically give you E theta equals 0 in equation 21, that is here, okay. So, you will get only for the H plane you can write G H and theta, because phi is 0 in this case. So, that is basically you are getting it from here. Okay. So, you are applying a limit of phi going to 0 on this particular expression that we have seen in equation 21, and this gives you 1 plus cos theta whole square divided by 4 into sin square w by lambda naught into sin theta. And if you want to find it out for the normalized gain for the E plane, you have to set phi equals 90 degree. In that case, you will get E phi equals 0. Okay. So, you can again do the same exercise. So, you can write G E theta. So, in this case the limit is basically phi going to 90 degree. You apply it on this generalized gain, okay, G phi theta, and this gives you 1 plus cos theta whole squared by 4. So, same fraction remains here. This is sin square, but then here it is L divided by lambda naught into sin theta. Okay. So, the performance assessment will primarily evaluate this normalized gain along the two principal planes, that is H plane and E plane, to assess the overall performance of the antenna. And this also includes the estimation of the antenna efficiency and the maximum power gain. So, now let us look into different design models of microwave antenna. So, let us create a simple design of a rectangular patch antenna with dielectric substrate. So, it is assumed that the substrate can be created from RT Duroid 5880, which has got a relative permittivity of 2.2, okay, and the antenna operates at the resonance frequency of 7.3 gigahertz, and we can also assume the substrate thickness to be D equals 0.0008 meter. Okay. Now, using these equations, okay, that tells you about the epsilon R effective, that is the effective relative permittivity, which correlates the width and the length of the antenna. So, you can do that and you can obtain the length to be 0.0132 meter and width to be 0.16 meter. Okay, that is obtained from these equations for this performance parameter, right. So, D is already given, the resonance frequency, okay, that is FR, okay, and epsilon R is also given. So, you can obtain this. Now, the dimensions of the antenna with composite substrate is same as the dimensions of the antenna with dielectric substrate, right. So, let us evaluate the material parameters of the composite substrate, that is the epsilon m, mu m and r. Okay. So, all those things, r is basically the wear radius. Okay. So, we can calculate those assuming that the copper wires are having circular cross section. Okay. And in order to do that, you can take into account the mentioned use of composites or metamaterials. So, this is due to the idea of tuning the effective frequency dependent relative permittivity and relative permeability of these artificial materials by individually adjusting the dimensions of the electric and magnetic resonance inclusions made in the unit cell. So, this is why the values of epsilon m, mu m and r can be evaluated using the effective medium theory. So, if you use that, you can calculate the relative permittivity to be equal to 2, relative permeability will be close to 1, and you can obtain the wear radius to be 0.00009 meter, right. So, in this study they actually used finite difference time domain, that is FDTD simulations of S11 spectra, and the far fields were calculated in E and H plane, also that evaluated the efficiency, power gain and the near field intensity, okay, around them. Now, what does the antenna design model considered? So, here 4 different design models were considered in this study. The first model considers the FDTD simulation for patch antenna with dielectric substrate, So, let us call it standard homogeneous numerical model. Okay. The second model basically corresponds to FDTD simulation for patch antenna with composite substrate. So, we will call it standard inhomogeneous numerical model or design. The third model basically assumes the FDTD simulations for the miniaturized patch antenna, okay, with composite substrate obtained, which we will discuss in the next lecture. So, we will call this as miniaturized inhomogeneous numerical model. And finally, the fourth model considers the analytical simulations using derived equations for patch antenna with composite substrate. So, we will call it standard inhomogeneous analytical model or design. So, we will now use the above given classification of antennas throughout the study. So, the commercial FDTD software Planck FDTD was basically used in this particular study as reported in this book, okay, for making the numerical simulations. So, in fact, the earlier obtained values of radius, then this pitch d, epsilon m, mu m, fr, L and w are being used in the parameter settings of the software for performing this above mentioned FDTD simulations for evaluating the antenna performance. The results you can see here, okay, the results of the FDTD simulations of S11 spectra for all the considered models are shown here. So, here you can see that A, the blue line basically tells you about the standard homogeneous numerical model. Okay. This dashed line, that is B, tells you about standard inhomogeneous numerical model, and the dotted line, okay, is basically from the miniaturized inhomogeneous numerical model, right. So, what you see here, that there is a peak, and throughout this study we are going to call this any peak that is appearing first as the main peak, and as you can see, the first peak in the S11 spectrum, okay, of each of this numerical model is basically shifted from the theoretical peak of 7.3. Okay. So, it basically comes from the effect that there is this fringe effect on the patch edges which are not accounted for. Also, there are spatial dispersion in the case of homogeneous models, right. So, indeed the numerical model with the dielectric substrate resonates at 7.307 gigahertz and the composite substrate basically resonates at 7.385 gigahertz, right. So, theoretically they were supposed to be close to 7.3 gigahertz. Now, here note that this the proposed analytical model does not take into account the fringe effects on the edges of the patch, okay, and therefore, by replacing a homogeneous high permittivity dielectric substrate with a inhomogeneous metal dielectric composite or metamaterial with the same value of both effective relative permittivity and permeability, will lead to redistribution of the effective will lead to redistribution of the reactive part of the load antenna impedance. Therefore, by replacing a homogeneous high permittivity dielectric substrate with an inhomogeneous metal dielectric composite metamaterial with the same values of both effective relative permittivity and permeability, leads to redistribution of the reactive part of load antenna impedance between patch and metal inclusions. Okay. So, it results in increasing the energy stored in the EM field radiated by the antenna due to a more effective use of the magnetic component of the radiated EM field compared to the case of the antenna with dielectric substrate. We can also observe from the figure that the antenna with composite substrate is better than the impedance matched, okay, than the antenna with the dielectric substrate. So, you can see a better dip in the S11 spectrum, right. So, you need to keep these points in mind as these are important, and with this we will stop here, and in the next lecture we will talk about miniature edge design and far field pattern in the H plane and E plane for all these antenna models. So, thank you. If you have got any query regarding this lecture, drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.